Okay, so we're creating an LC circuit. So here is our inductor, and here is our capacitor. And we argue that despite the time dependence, there are charged particles that move around, and if we only take into account the charged particles that have electric fields that diverge radially away from them or towards them, then this principle applies, and that means the total voltage difference around the circuit is zero. And so we look at the voltage across the inductor, which is L di dt, so VL, and voltage across the capacitor, which is charge over the capacitance. The sum of these two must be equal to zero. Okay, so that's what, so this looks like L di dt plus Q over C equals zero, and that's our principle. It's conservation of energy. So we want to solve this equation, but notice that I is, by definition, dq by dt, and so our equation really reads L d2q by dt squared plus q over c equals 0. And we can write this in the form where we isolate the second time derivative of the charge, plus there's a constant in front of the q, and that's equal to 0. We could solve that equation. It's fairly straightforward, but it's interesting to notice that this is the same as the simple harmonic oscillator. Simple harmonic oscillator, SHO, where we have the position of the oscillator is determined by an amplitude times the cosine of the angular frequency times time plus some initial angular position, phi. So if I take we want to show that I get two time derivatives of this, I'll end up having an equation that looks exactly like that, and therefore that the solution to Q has to be similar to the X solution. So charge and position are analogous. That's what we want to show. So dx by dt is equal to minus omega times the amplitude x naught times the sine of omega t plus phi, and the second time derivative gives us the same quantity back, but with a minus omega squared x naught cosine of omega t plus phi. But notice that this is minus omega squared times x itself, and so in other words, what we've just shown is that we have this equation here for x solves this equation. Let's bring this to the other side, plus omega squared times x equals 0. And so this is the solution to this equation. We just went the other way around. We derived the equation, meaning something that has two derivatives in time, and its solution is this, but this equation here has the same form as this equation here. Right? It's two time derivatives of some quantity. In this case, it's position x. In this case, it's charge q, plus some constant, right here, 1 over LC, and here omega squared. These are just two constants in front of the quantity itself. In this case, it's the position. In this case, it's the charge. So the solution here can be just read off from this. It has to be charge is some, we could call it Q naught, right, or some other quantity, but we physically can figure out what that means. Cosine of, so it would be an omega t plus phi, but the omega, so here we have an omega squared, and omega appears here, But that is 1 over the square root of LC, which we square, which get 1 over LC. So here we must have a t over LC square root plus a phi. So that's the solution. We've just found that, or really argued by analogy, that the solution for the charge on the capacitor behaves like this. In other words, it oscillates in time according to a cosine. And the current in the circuit or through the inductor, which is by definition dq by dt, also oscillates. That's just the derivative of this. We get minus q naught over LC square root times the sine of t over LC square root plus phi. So this is the behavior of the current in the circuit. And we see that they're both oscillating, but notice that when Q is equal to Q naught, right? So when this whole quantity here, the cosine is 1, Q is equal to Q naught. But when the cosine of something is 1, then the sine of that quantity will be 0. And so we have that the current is 0. And when the charge on the capacitor is not Q naught but 0, so that the cosine of something gives us 0, then the sine will not give us 0. This thing can be 1, and then the current is not 0. It could be this quantity here, and that would be the maximum possible value, but with one sign. In this case, it's the negative sign. So really, this equation here can be written as I equals I naught sine of t over LC plus phi. And basically what we're seeing is that when we have a fully charged capacitor in an LC circuit, there's no current in the circuit. And when the current is the maximum value that it can be in the circuit, the capacitor has no charge. And so these things are oscillating. And we'll look into this in more detail.